Welcome to lecture 29. In this lecture, I will discuss so-called Graßmann variables, which are non-commuting variables. Recall that normal numbers are commuting so that the product AB is the same as the product of BA. However, there is no reason not to consider a different commutation rule, in particular anti-commutation rule, such that the product AB is equal to minus B times A. The corresponding numbers that fulfill this anti-commutation rule are called Graßmann numbers. In the English, the letter S here is sort of spelled out as a double S, which is sort of explaining the different notation. And these are the numbers that I will be talking about in this lecture. An important consequence of the anti-commutation relation is the so-called nilpotence rule. So if you take this equation 29.2 and you apply it to the same variable a, you get that a times a is minus a times a. So a squared is minus a squared. Since the only variable that fulfills this commutation rule is 0, you find that a squared, and consequently also a cubed, a4, and any higher power than 2 will have to be equal to 0. It is possible to represent these Graßmann numbers as matrices. In particular, if we have two Graßmann numbers, θ1 and θ2, we can find the representation in terms of 4 by 4 matrices. These are listed in equation 29.4. And it is straightforward to verify that these fulfill the anti-commutation rules. In particular, the square of the matrix θ1 is 0, the square of the matrix θ2 is 0, and θ1 times θ2 is equal to minus θ2 times θ1. As a consequence of the nilpotence, the Taylor expansion of any function that is a function of a Graßmann variable θ terminates after the second term. So usually, if we have a function f of θ, we can Taylor expand this function in a power series of θ, but nilpotence says that all terms higher than θ squared have to vanish. So that means that the Taylor series terminates after the coefficient C1, where C0 and C1 are usual numbers, commuting coefficients, or also sometimes called C numbers. A surprising consequence of the nilpotence will be the somewhat unusual integration rule for Graßmann numbers, which we'll come to. In particular, if we consider the Graßmann integral dθ of f of θ, which, because of the Taylor expansion, is equal to the integral over dθ of the Taylor expansion up to linear order in θ, we can write this integral in terms of its result. The result has to be a function of the variables c0 and c1, and we'll come to the form of this variable in a moment. Because the integral is a linear function in c1 and c2, the result f must also be a linear function. So f has to be equal to c0 and c1 multiplied by constants alpha and beta, where alpha and beta are ordinary numbers. If in addition we require that there's a symmetry of the integrand under translations, so basically if you think that this integral, for instance, is an infinite integral, we can shift the integral by a constant. This doesn't do anything to the measure, so the measure dθ stays the same under translations, and the function here will be a function that has the corresponding coefficient c1 multiplied by the sum of the original θ plus an external Graßmann variable eta. So we find that the original function f of c0 and c1 must be equal to a function where, since in this case the only combination that's relevant is or let's put it this way, the integral here has a term that is linear in θ, that's the term c1, so that's our original f of c1, but the term that's not proportional to θ is now c0 plus c1 eta, so that must be the result that we have on the right-hand side. So we find that our original function f of c0 and c1 must be equal to f of c0 plus eta c1 on the right-hand side. Since f is a linear function, you can plug this in to equation 29.9, and you find that this coefficient alpha here has to be 0, because that's the only choice that we have, that f of c0 and f of c0 plus eta c1 has to be the same. Beta in principle could be arbitrary, but it is customary to normalize the coefficient beta to 1. So using this normalization, we find the integration rule that the integration d theta of c0 plus c1 theta is equal to c1. And as a consequence, we find that the, let me sort of go back. So that means that the integration d theta of something that does not depend on the Graßmann variable is 0. So that is the first result here. We have the integration of unity vanishes. And the second is that the integration of something that contains the variable theta is equal to the coefficient multiplying this linear variable here. So we find that d theta theta is equal to 1. You should note that these are unusual integration rules, and in fact, they actually correspond to something that's more customary seen in differentiation. So if you compare the differentiation rules for usual variables, you have that the derivative of a constant vanishes, the same as the Graßmann integration of unity vanishing, and that the derivative of a function linear in x is equal to 1. That's the same as the integration rule of the function theta is equal to 1. If we have two different Graßmann variables, theta and eta, we can build up equations and integrations of multiple Graßmann variables. Clearly, if they're both Graßmann, then they still fulfill the anti-commutation relation, which I express in terms of this curly bracket here. And two-dimensional integrals are then given as an integral over d eta and d theta of a function of these two variables. And the integration measures d eta and d theta also obey this anti-commutation rule. So in particular, the anti-commutator d eta d theta vanishes, the anti-commutator between d theta and theta vanishes, as does the anti-commutator between eta and d theta. We can consider the under quotes Gaussian integral d theta d eta of e to the minus eta b theta, where I took b to be an ordinary C number. We can Taylor expand the exponential to linear order because all higher order terms vanish. So we get that this is equal to integral d eta d theta of 1 minus eta b theta. We can pull the b through because it's a C number, it doesn't depend on either Graßmann variable. And then we have to take into account the anti-commutation rules. To pull the eta through the d theta, we'll get a minus sign. So we end up with an integral d eta eta and an integral d theta theta, both of which, according to our integration rules that we found at the previous slide, are unity. So we find that this whole result, this whole integral here, is just equal to b. We can generalize this result to multidimensional integrals where we integrate over multiple Graßmann variables, eta, I, 1, 2, 3, 4, and so on, multiple integral theta, 1, 2, 3, and so on, times the exponential of something that now has a Gaussian form with a matrix, C-numbered matrix Bij. And if you use the same expansions as before, you find that we can shift the variables eta and theta such that this becomes an exponential that involves the eigenvalues of the matrix B. So just as we have one eigenvalue B here, we get the product of eigenvalues from this integration, and we find that this is equal to the determinant of the matrix Bij in the integral. And this concludes the present lecture.